Hello. So today we'll talk about the magnetic circuit of chapter 3. Let me see whether do I have a highlight. Yeah, I have pen, laser pointer. Okay. So today we will talk about electrical power technology. Chapter 3, magnetic circuit on electrical power technology. So introduction to magnetic circuits. Magnetic and electromagnetic effects play an important role in the design of electrical electronic systems, such as motors, generators, transformers, and loudspeakers, etc. Most of the equipment depend on the magnetic effects to function properly. This is a great deal of a similarity between the analysis of an electric circuit and magnetic circuit. For example, magnetic flux, which is an analogous. Analogous means equivalent to the current. Magnetomotive force, which is equivalent to the voltage. And then so magnetic circuit. Actually, when we talk about magnetic circuit, we need to relate to the material. So we can see this is a core. Then this is a winding. When we inject current into this winding, a flux will be generated by using Fleming right-hand rules. Fleming right-hand rules. So it will create a flux in the core and flowing from one point to another point in the core material. That's why it involves material. And this is a LC. LC is a mean path length. The flux that's flowing through from this point begin and then go back to this point. This is the total length. We can put in an equivalent circuit. We would like to make the engineering problems become simpler. So we put in an equivalent circuit. We call magnetic circuit. In an electric circuit, when we have a battery, we have a current flowing through. We have a resistor that connected to a battery. There will be a current flowing through in the circuit. We call electric circuit. But at the time that when we want to make a complex problem to become simpler, we put this magnetic material into magnetic circuit. It is a circuit, but it is come from magnetic. That's why we call magnetic. This circuit is come from electric, so we call electric circuit. So we can put analogous or equivalent. For example, this is the source to create the flux. So we have an MMF generated with the positive at the top, negative at the bottom, so that the flux is flowing through from here, then going back to this side. Then this is the we call reluctance instead of a resistance. So we have a equivalent circuit. Then this is a simple magnetic core. Core is made by steel. So when there's a current injected into this core with the entrance, then the flux will be produced inside the core. And then we only take the mean path. Mean path means if let's say this is a 10 cm, we take from 5 cm here. If this is a 20 cm, this is at the location will be the 10 cm. Or mean, we take the average. Okay. Actually, we have a lot of flux going through. We have a lot of flux going through this side. For example, from here to here to here to here. Why we don't choose this one? But why we don't choose the red color flux path? Path means the root. And then why we choose the center one? Actually, we just want to make it average. That's why we take the center one. So then go back to the laser pointer. So when there's a flux flowing through, we actually need to focus on the cross-sectional area. We need to know how the flux flowing through from how the flux crossing. The flux actually need to cross to the area which is 90 degree. For example, this is the flux flowing through, then it must be 90 degree to this plane. For example, like this. But we only choose the mean path. Mean average path. So we can compare next we compare the electric circuit and the magnetic circuit. Electric circuit, as usual, it comes from the battery voltage. For the magnetic circuit, the exciting force is actually from the ampere turns. And then the response, when we input the so-called, let me choose can when we input the battery, okay, the current will flow into through the resistor. Or we have a current, then we have a flux. When we have a MMF here, okay, this is MMF here, then we have flux will created. Okay, this is flux. Then for electric circuit, it complies Ohm's law. Complies Ohm's law, V equals to IR. Same as well. For the magnetic circuit, we have F equals to flux equals to MMF, magnetomotive force, divided by reluctance. Reluctance can be S or can be R, for example here. Sorry, I should come back here. When we make this circuit equivalent to the electric circuit, we have an EMF battery, we have a resistor, we have a current. Then for the magnetic circuit, we have MMF, we have a reluctance, we have a flux. So if I go through one by one, okay, for electric circuit, we have a battery voltage, we have a current, we have a V equals to IR, Ohm's law. By dimension, if let's say we want to find the resistance, we have a R equals to rho L divided by A, or the conductance is 1 over R. I guess you're all very good in this. Then we have a proportionality, which is the rho, and also we have a field intensity, where we call it as an electric field intensity in volt per meter, where it is a V divided by L. It is a volt per meter. Density will be the current density ampere per meter square. So this is what we know actually from the electric circuit. Then when we want to make into analogous to magnetic circuit. Magnetic circuit, we have a coil, create a flux flowing through the magnetic core. See, when you talk about magnetic, it is revolved material. Then we want to put this thing into a simple circuit. So we have an MMF, which is generated by number of turns times the current, we call Ni. Then if flowing through inside the core, then the core create the reluctance. Okay, have the reluctance, then there's a flux flowing through inside the core. That's why when we come to the comparison, as compared to the battery voltage, where in the magnetic circuit we have ampere turns. For the response, we have a current, but in the magnetic circuit, it is a flux. For the Ohm's law, V equals to IR, same as well, it will be F equals to 5R. F equals to 5R. Where F is an MMF, magnetomotive force. The force generated by the magnetic effect, magnetomotive force. Then R will be reluctance, or here it use S. Then phi will be our flux. This is the phi. Then the dimension, electric circuit, we have R equals to rho L over A. For the reluctance, we have a rho L over mu A. We'll go indeed inside this slide. Proportionality, we have a 1 over mu R, 1 over mu. And the field intensity, we have E over L in the volt per meter. For the magnetic field intensity, this one is magnetic field, this one electric field. Magnetic field intensity, we have a Ni over L, which is a ampere turns per meter. Ni is equivalent to my magnetomotive force, E is equivalent to my battery voltage. So, in the density wise, electric circuit, we are talking about current density, but in the magnetic circuit, we talk about flux density. This is how the comparison between the electric circuit and the magnetic circuit. Next, so just a brief summary, briefly about the magnetic field. So what is a magnetic field? A magnetic field can be produced by putting a current through a coil, as shown before. And what is magnetic induction? It occurs when a material is subjected to a magnetic field and is changed in the magnetic moment from electrolysis. Electrolysis is more on the so-called material science. Here we talk about a big material science. Then the types of a material response to a field are, we have several types. We have a ferri or ferromagnetic, large magnetic induction. We have we have a paramagnetic, poor magnetic induction. Paramagnetic is for the material with a poor magnetic induction. Diamagnetic is opposing magnetic moment. It creates the magnetic field which is opposing it. Then we have two types. Is a hard magnet with a large coercivity. We have a soft magnet with a soft coercivity. Hard magnet is something like a permanent magnet. Soft magnet is temporary. I think it's a no. Later we can go to the next part. Magnetic induction. So yeah, just now we have basically we have three types. This graph will talk about the BS curve. I think magnetic induction versus the strength of the applied magnetic field, which is in the ampere turns per meter. No worry about the unit, we'll summarize later on. So if by comparison, the diamagnetic where the material is from copper, what is this? Silicon, zinc. It is a very low VH value. The vacuum is almost zero. Then the paramagnetic have we have aluminum, chromium, or titanium. Then ferromagnetic we have a ferrite oxide, nickel ferrite oxide, or ferrimagnetic. For example, the ferrite, cobalt, nickel. So we can see the magnetic field is stronger here. Induction is stronger here. Yeah, actually in this subject, during your lab session, you will go through the EPSTEIN test. EPSTEIN test is for us to measure the power loss of the electrical steel material, and then for us to plot power losses for electrical steel material, and also we can measure the leakage flux. No. Then the voltage will be calculated by using this equation is V equals to 4.44 TNFA lah. Then we actually can derive this value, but not now. I have included the video in the EPSTEIN test in the e-learning. Please have a look. It explains more detail what is the laboratory talk about. And then we have a single sheet tester as well in this subject. This tester is for us to know the easy and the hard direction in the steel strips. And then we will use the search coil as one method to measure the induced voltage. And then we will measure the nominal loss along easy and hard direction using the iron loss tester. As well, before we want to run the lab, we need to calculate what is the input voltage for us to measure all the flux value. I think so. All the voltages generated from injecting this voltage. Same as well. The video of how to about the single sheet tester has been prepared in the e-learning. Please have a look. And then yeah, come back to the magnetic circuit. Next, we'll talk about flux. So in a magnetic circuit is a closed path for the passage of a flux produced by the magnetic force. This is the magnetic force, and then it is a closed path we call magnetic fuse line. Okay, and then the lines of force in the magnetic field are called magnetic flux. The line of force here, this one is the magnetic flux. Okay, from north to the south, north to the south. North will be always outward, south will be always inward. Then whereby the total lines of force in the magnetic circuit are produced by magneto-motive force. The general direction for the magnetic flux flow is from the north to the south pole. And then the flux is in a unit of phi. This is pronounced by phi. And then the flux is in a symbol. The symbol of flux is phi. And then the unit is the meter. So we need to put in the equation. So flux density is defined as the flux per unit area. So this is the flux per unit area B. So B is the unit of the Tesla, which is the standard. Magnetic flux is in the Weber area of the meter square. And then the strength of the magnetic field measured by flux. A good way to think about is by measure how many field lines in a certain area. By using the flux density, there is a stronger field at the pole where there are more field lines. A magnetic field is often called as a symbol P. And then the unit for B, usually we use Tesla instead of a Weber per meter square. Okay, let's go to the example. For the core in the figure below, determine the flux density in Tesla. Okay, use the previous equation, B flux divided by A. So, given the flux is going through in the magnetic core, this is the material in the magnetic core, and we only take the mean path, which is the center of the core, which crosses 90 degrees. Okay, the flux line must crosses 90 degrees. Okay, the flux line cannot crosses like this. The flux line cannot crosses like this. This is wrong. It must crosses 90 degrees. Right? Okay, it's 90 degrees. So given the flux is 6 times 10 to the power minus 5 Weber, area will be 1.2 times 10 to the power minus 3. So I put inside this one. I calculate, I have 0.05 Tesla. So this is how we calculate the magnetic flux density. So permeability. Permeability is the ability of a magnetic material to produce a flux in a magnetic circuit formed by a magnetization force. So actually I want to stress this permeability is the ability of a material, okay, to produce a flux when we have a magnetization force. And the material is said to have a high permeability when there's more flux can flow through it. And then the symbol will be mu. And then the unit will be Weber per ampere meter. And then we have three types of permeability. Permeability of a material, mu. And then we have permeability of free space or vacuum, we call it as air or vacuum, mu naught. And the unit will be 4 pi 10 to the power minus 7. Then we have a relative permeability mu r, the ratio of permeability material to the permeability of a free space, which is mu r equals to mu divided by mu naught. So the ferromagnetic materials have a very high level of permeability. High level of permeability means a lot of fluxes are flowing through in the materials. Then permeability of all permeability of all non-magnetic materials, for example, non-magnetic material, for example, copper, aluminum, wood, glass, and air is the same as for free space. Ferromagnetic material, mu r, which is more than 100. Non-ferromagnetic material, mu r usually is almost equal to 1. Remember this one, it's very important. So reluctance. Reluctance is the resistance to flow of magnetic flux. In the electric circuit, we have a resistance. Resistance is used to retard the current. Reluctance is used to stop the, to resist the flow of magnetic flux. In an electric circuit, resistance resists the flow of a current. By analogy, in magnetic circuit, reluctance resists the resistance of the magnetic flux. Reluctance depends on the length of the material, cross-sectional area of material, permeability of the material. Then we have R equals to L over mu A. We call as a Wells or ampere turns per Weber. So L over mu A. Mu equals to mu R times mu naught. So Ohm's law for magnetic circuit is actually V equals to IR, or F equals to phi R. Or return, phi equals to F divided by R. Phi is a magnetic flux in Weber, F is a magnetomotive force, ampere turns, R is a reluctance, ampere turns per Weber. Unit is very important, please remember. The magnetomotive force, the force created by magnetic field, and then generate the force, is proportional to the product of the number of turns around the core in which the flux is to be established and the current through the turns of 1 year. So we have F equals to Ni. N is number of turns. I is the ampere. That's why ampere times turn becomes AT, where it is a magnetomotive force. We can do some comparison. For example, Ohm's law for magnetic circuit. We have Ohm's law in electrical and magnetic circuit. That's why in a circuit we have two. One is electrical, one is magnetic. In electrical, we have a voltage, we have a resistance. When we connect it together, a current will flowing through inside. Then we have a V equals to IR. Analogy means equivalently or analogous or equivalent. It's not the same, but similar. Or in terms of the concept, we use equivalent. So Ohm's law in a magnetic circuit. We use same as well. We generate the flux by using a coil, by injecting the current inside in the coil. Then it will generate flux. Flux will flow through material. What is the material? It can be a magnetic material in this core. So it can flow through the steel. Then steel is one of the material. Air also one of the material. Then steel back, and then coming back here. So we have a force which is generated by magnetomotive force, and then we have a reluctance here. Then we can generate a flux flowing from this side to the end. So F equals to 5R. That's why we have a Ohm's law in electrical, Ohm's law for magnetic circuit. So magnetic field intensity, magnetizing force. The magnetomotive force per unit length we call as the magnetic field intensity. So H equals to F over L as well. Just now we have F flux equals to phi equals to F divided by R reluctance. Now we have a H equals to F divided by L, AP over M, ampere turns per meter. Magnetic field intensity H is determined solely by the number of turns and the current of the length of the core. So H equals to Ni over L here, this one. Then the flux density and the magnetic field intensity are related by the equation B equals to mu H. Later on I will summarize it, okay? Let's go for example on how to use all the equation. Find the value of I needed to develop a magnetic flux of the 4 times 10 to the power minus 4 Weber. So for example, this is a ring, and then the cross-sectional area given is 2 times 10 to the power minus 3 meter square. N is a 400 turns. I length is a 0.16 meter. Means from here, okay, go back to that point. This is a 0.16 meter. So now, what they want? They want the value of I. Is it? I. The value of I. Where is I? How come no I? Oh, it's at the back. So first, we'll find the flux density, or phi equal divided by A, whereby it's a 4 times 10 to the power minus 4 is given here. Okay, this is a flux. Divided by the area is here. Equals to 0.2 Tesla. Then we use H equals to B over mu. B is a 0.2 Tesla. Divided by 1.816 times 10 to the power minus 3, which is the mu, is given here. Equals to 110 ampere turns per meter. So we have calculated B, we have calculated H. Next, we will calculate using this equation F equals to Ni equals to HL. Then we want to find I. So we use a HL divided by N. H calculated, L is given 0.16 meter. Then N is given 400. So becomes 44 milliampere. So this is the current needed so that I can get I can generate the so-called the flux density, the flux of 4 times 10 to the power minus 4 Weber. So example 3, please go back and have a try. A coil over 200 turns is wound uniformly over a wooden ring, having a mean circumferential of a 600 mm, and a uniform cross-sectional area of a 500 mm square. Oh, this is circumscribed. If the current through the coil is 4 ampere, we need to calculate the magnetic field strength, H, and then we need to calculate the flux density, B. We also need to calculate the total flux, where phi. Have a try, Same as well. Example 4. Go back, try. Maybe we'll discuss later during the opening session. So hysteresis. Hysteresis is the lagging effect between the flux density B of a material and the magnetizing force H applied. The entire curve shaded is called the hysteresis curve. Hysteresis curve. This shaded means the blue color lah. This is hysteresis curve. So if the material starting, it is not applied under any. This is called BH curve. B is a y-axis, H is a x-axis. So BH curve. So when we apply current, you see H is proportional to the current. If the material is new lah, not yet applied to any current, and now we apply the current, it will go to this line. So if I increase the current, it will go up until it saturates. Then if I give opposite direction of the magnetic field, it will go in to here until the magnetic field is 0. Then after that, if I apply a negative magnetic field, it will go in. B will go to the negative side, this plane. Same as well, if I reduce a magnetic field in opposite direction, it will come back to 0. I mean the magnetic field H is 0. Then when I apply again positive H, so the B will increase until here. Okay. Then if there is no H applied, for example, if my H is 0 after applying this curve for that material, if it is a permanent magnet, if there's no H is 0, then this is the magnet that we have. That's why when we put in a permanent magnet, even though we don't put any current, it will have its own magnet. Then the density that it has, or the strength that it has, we call Br. This is called Br. So normal high magnetization curve for 3 ferromagnetic materials, which are normally we use 3 types: sheet steel, cast steel, and cast iron. So we can see that the BH curve, cast iron is here, cast steel is this one, steel sheet is this one. So we can see that actually the steel sheet has a higher permeability, because you see, for example, if I only apply the H for 300 ampere turns per meter, I can get B about 1 point something Tesla. Here I only get 0.6 Tesla, and here I don't even get 0.2 Tesla. So we can see that how good the flux can flow in through in this material if I only apply the same current or same magnetic field. Okay, so how to read this chart? So for example, if let's say I want to read steel sheet, given that now the B is a 1 Tesla, so how much the magnetic field that I need to apply to get the 1 Tesla? So I need to check here. If I want to get 1 Tesla, I need to apply about 180 ampere turns per meter. Same as well for cast iron. If let's say I want to get 0.68 Tesla, how much the magnetic or I should say like this: if I apply 2640 ampere turns per meter of the magnetic field on that material, so how good is the magnetic flux density retained inside, occupied inside the material? From this chart, we have a 0.68 Tesla. This is how we read the BH curve. Next, we will correlate with the Ampere circuital laws. Just now we have Ohm's law. Now we will link with the Ampere circuital law to apply more in depth. So Ampere's circuital law, the algebraic sum, saying that the algebraic sum of the rises and drops of the MMF around a closed loop of a magnetic circuit is equal to 0. Means if let's say I have a 2 MMF, here I have a 10 ampere, here must be negative 10 ampere. It is principle of conservation of energy. It must be the same. One rise, one must be dropped. Okay, and this is the sum of the rises in MMF. MMF means magnetomotive force, equal to the sum drops in the MMF around the closed loop. So put in the mathematics, summation of the force, it must be equals to 0, where F equals to HL. By applying the relationship for electric circuit, F equals to IR. However, F equals HL is more practical equation for the MMF drop. For example, total F must be 0, where equals to F equals to HL. So, you see, when we talk about magnetic circuit, the first thing comes to the mind, it must be magnetic material. What is the material inside? So, what is material inside? We have a solenoid with a current. So, current excited in the coil, and then it creates flux, flowing through where? Flowing through iron, steel, cobalt, and then come back to the iron. Can it flow through the air? Yes, answer is yes. So from this example, we have three types of materials. One is iron, one is steel, one is cobalt. So by applying the Ampere's law, circuital law, so Ni, this one, this coil will generate MMF, magnetomotive force. What is generated here will distributed here, whereby Ni equals to H, the magnetic field intensity, crossing intensity plus magnetic field crossing the length of the material. So we have for example, now we go Ni. We see the second equation, which will be easier. Ni generated will distribute to the steel, cobalt, and iron. So what is the equation for the steel? We have HAB times LAB. So A, B. Steel, A to B. We take the length from A to B, the mean length, and the H inside times the L. Why we have a HAB, HBC, HCA? Why it is not only H? That's why we talk about material. Different material have a different permeability, and different permeability will have a different magnetic field. That's why we have a different H. So we split into three things. One is a steel, one is cobalt, one is the iron. So HAB times LAB, this one. HBC times LBC, this one. Then we have a HCA times LCA. So when you add up these three together, it will come from the Ni, Principle Conservation of Energy, PCE, right? For sure. There's there's a source, it will distribute it to other places. Okay? Then when we move from the right hand side to the left hand side, we actually found this equation. And this equation reflects to top one. Okay? So Ni minus HAB, the steel one, minus HL, cobalt one, minus HL, iron one, it must become 0. It must be 0. So the sum of the fluxes entering a junction is equal to the sum of the fluxes leaving a junction, which is the same as Kirchhoff's current law. When IA come in, become IB and IC, so IA will equals to IB plus IC. So same as well. Flux A come in, it will be equal to flux B and flux C, depend on the arrow lah. Then flux B come in, plus flux C, it becomes flux A. So flux A equals to flux B plus flux C at the junction A. This one, flux A, flux B, flux C. Junction B. So in, out. B plus C become A. B plus C become A. Okay? Again, the spreading of the flux line outside the common area of the core or the air gap in the figure below is known as a fringing. Okay, this type is normal because all the flux from this leg crossing to the air and then to another leg is straight. It is a normal. Crossing straight is normal. But when it's crossing outside of a straight line, we call fringing. It fringe. Fringing. Which means that the spreading of the flux line outside the common area. This is a common area. It is outside. We call fringing. Air gap is used to avoid saturation to occur in magnetic material. Yeah. actually we don't want to make all the fluxes. If let's say we don't want to make the magnetic material saturate here, we need to reduce the fluxes here. So air gap is used to avoid saturation to occur in magnetic material when the current flow in is too high, and the air gap will increase the reluctance of the magnetic circuit. At a simple way, if let's say we don't want to make it saturate, we need to push more fluxes here. This is how we put a air gap. Then we will use an example, the calculation to see why we impose the air gap, then the saturation will be reduced in the magnetic material. By the way, saturation in the magnetic material is not good. It will cause a lot of losses. And also the saturation will be here. This is called saturation. When there's too many fluxes flowing through in the magnetic material, this is saturate. Then when it saturates, it will contribute a lot of losses. That's why we don't want. And then this is one way of how to reduce the losses. So equivalent magnetic circuit with the air gap. So same as well, I have a magnetomotive force F. We have a reluctance of the core and also the air gap. Then we have fluxes, all in a mean length. So when we put into the magnetic circuit, this is Ni. Then I have a reluctance of the core. Then I have my reluctance of the air gap here. This one is a HgLg. Hg is a magnetic field of the air gap and also length of the air gap. So this is a typical magnetic circuit and equivalent magnetic electric circuit. Sorry, this is not electric circuit. This is magnetic circuit here. So the core reluctance is Lc divided by mu Ca. So have a look. Even the same equation we have. Air gap reluctance R equals to Lg divided by mu naught A. So have a look. Even we are using the same equation, but we need to mention very clearly. Lc means the main length of the core. Mu C is the material of the core. Lg is the length of the air gap. Mu naught, why we only use mu naught instead of mu g? Actually mu g equals to mu r times mu naught. But mu r of the gap or of the air is 1. So mu equals to mu naught. That's why we directly use mu naught. Area possibly will be the same. If the cross-sectional area will be the same. So when we put inside in Ampere's circuital law, Ni equals to flux times Rc plus Rg. I guess you are all very expert in this one. So fringing effect. Just now we talked about so we talked about fringing effect. Flux that flow through the air gap will tend to bend from its original direction where the flux inclined to expand at the fringe. So this is common area, the blue color one. Then when it want to expand, this is the red color, fringing magnetic fluxes. Magnetic flux in the air, this is common area. So this is a fringing effect. Parts of magnetic circuit. So when I have a material, something slot inside here, actually it's a movement from this one to the solid line one. Okay. It will cause increase of the cross-sectional area of magnetic path in the air gap with respect to the cross-sectional area of the core. So if we go back to here, which means common area, for example, it is only a blue color side. If let's say all the fluxes, if let's say we don't talk about fringing effect, all the fluxes will passing through only the blue color. But if we consider the fringing effect, the area will expand until the red color side. That's why when we have a air gap, we need to be careful whether the question is involved fringing effect or not fringing effect. If fringing effect, the area will be different. Once the area will be different, the reluctance will be different. Okay, so be careful. So have a look on the example 5. Calculate the magnetomotive force F required to produce a flux of 0.015 Weber flux across an air gap 2.5 mm long, L, having effective area. Effective area means the area that take effect Usually when we consider the fringing effect, then we need to recalculate the area. We have a common area, then we have an effective area of 200 centimeter square. So the answer is 1492 ampere turns. So what is the equation that we use? F equals to 5R. We have a 5. This is flux. We have a L. R is a L over mu A, mu naught A. L long is 2.5 mm. Mu A is 1. Mu naught is a 4 pi times 10 to the power minus 7. You need to memorize this one. 4 pi times to the power minus 7. It will not give. This value will not given in a paper examination. Then the area is a 200 times 10 to the power minus 4. Remember, 2.5 m, this is in millimeter. So pressing the calculator become 1492 ampere turns. So let's have a look on the example 6. So I have a current put into the coil, then created the fluxes, flow through the coil, and then flow through the air gap, and then going back. So given that the area of the coil is 9 times 10 to the power minus 4 meter square, the length of the air gap is 0.005 meter. Then the mean length of the coil is 0.3 meter, and then the mu r, the relative permeability of the material, is 70,000. So find the flux if the flux density is 1 Tesla. This one, 1 Tesla. The current in the coil. Find the current in the coil as well. Find the magnetic field intensity in the air gap and in a magnetic coil. Magnetic field intensity should be H. Neglect the fringing effect. So neglect the fringing effect means the area 9 times 10 to the power minus 4 in here will be the same as here. So AC equals to AG. Also, if I say, first thing, we must put into magnetic circuit. So we put into magnetic circuit F plus minus, plus at the top, minus at the bottom. Then flowing through the RC. RC means the reluctance of the coil. And then RG is the reluctance of the air gap. So we have 2. Then we need there's flux flowing through these things. Then given that AC equals to AG, AC means the cross-sectional area of the coil is the same as the cross-sectional area of the air gap, which is 9 times 10 to the power minus 4 meter square. The length of the air gap is 0.005 meter. The length of the coil is 0.3 meter. So the first thing, flux is equals to BA. So my B is 1 Tesla given, A is a given, then 9 times 2 10 power minus 4 Weber. So my F equals to flux RC times plus flux RG equals to FC plus FG. To find the current, we need to find the MMF. Use Ohm's law equivalent. So air gap, RG equals to LC divided mu naught over AG. Insert all the numbers, then we find Fg by 5 times R. So we have 5. In the coil, LC divided by mu R mu naught AC, same as well. So our Fc is like this. So Fc plus Fg become the total. Then I can find my current. So my total F is 401.31 divided by the number of turns of 500. So it becomes 0.8 ampere. Then I need to find the magnetic field intensity, where different material will have a different magnetic field intensity. So Hc, the core of the magnetic field intensity, is a B divided by mu R mu naught. B is a 1 Tesla, mu R is a 70,000, mu naught is a 4 pi times 10 to the power minus 7. So my Hc is this one. My Hg, same, but without mu R. Mu R is a 1. So I have this value. So we can see that the Hc in the core is much lower than the Hg. So we have an example 7 as well. Have a try. That we will discuss in the next session. Then maybe I've gone through first. Let's go through first. The figure represents the magnetic circuit of the relay. The coil has a 500 turns, this one 500 turns, and the mean core path is a LC, which is a 360 mm. This is a 360 mm. When the air gap length 1.5 mm here. A flux density of 0.8 Tesla is required to actuate the relay. This one we need 0.8 Tesla. Then the coil is cast steel. This is cast steel with a field intensity 510 of ampere turns per meter. Find the current in the coil. How much current do I need so that I can activate this relay? Compute the values of permeability and relative permeability of the core. If the air gap is 0, means no air gap here, find the current in the coil for the same flux density in the coil as well. So we also can do the series and parallel magnetic circuit. For example, different, I have a solenoid, I inject a current inside the core, then generate a flux here, then it will split into two sides. So flux 3, flux 1, flux 3, flux 2. So by using Kirchhoff's law, flux 3 is equal to flux 1 plus flux 2. This one. Then we also can, the first thing actually we need to put into magnetic circuit first. First, this is the MMF. Second, we have reluctance in the center limb. We have a second reluctance in here. Here is the first one here. First reluctance, second reluctance. This is the second reluctance. We have a third reluctance here. No air gap. Then we have a one source MMF. By applying the Kirchhoff's law, like in the electric circuit we call Kirchhoff voltage law, KVL. For the meshing number 1, so Ni, this one Ni equals to H3 times L3, this one, plus H1 plus L1 times L1. Same, Ni also same, H3 times L3 plus H2 times L2. This is loop 2. So we have a 3 equation. Then we can solve it. Just now the coil is in the middle. Now the coil is at the side. So I put into magnetic circuit first. I have a one source here. Then this is one reluctance. Second reluctance is here. Third reluctance is here. So flux 1 go in. Flux 3, flux 2. So flux 1 equals to flux 2 plus flux 3. This one. Then let's have a look on this loop. So Ni equals to H1L1 plus H3L3. So this one will be H3L3 equals to H2L2. Okay? This is another one with the air gap. So solenoid inside, I have a one reluctance, another reluctance, another reluctance. So reluctance 1, this is a source, reluctance 2, reluctance 3. Reluctance 2 here, reluctance 3 here. So the flux flowing from the center split to the left and right. So flux 1, flux 2, flux 3. So flux 3 equals to flux 1 plus flux 2. Okay? Then loop 1, Ni will be equals to H3 L3, or another reluctance is a G. H3L3 plus I think it's HGLG plus H1L1. Then second loop, Ni equals to H3L3. This one is US. HSLS plus H2L2. Okay. So as a brief summary for all equations, I make it simpler for you. You will use it after that. As overall, have a look on the ABC first. A, B, C, D, E. The first step when we talk about a magnetic circuit, remember, before you start to do the answering, please remember this equation first. F equals to 5R. So this is A. Second, what is F? F equals to Ni, also equals to HL. Second, B. C. Step C, we go to flux. Flux equals to BA. Then step D, B equals to mu H. Mu equals to mu R mu naught. C, D, E. Then R is a L over mu A. Mu equals to mu R mu naught. And then this A is interrelated. This H is interrelated. This mu is interrelated. So A, B, C, D, E, F first. Second, we need to list out the unit. or else when we want to answer all the questions, we always forget about the unit. So have a look on the numbering: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is how we use. I put it here for you to understand how to find the unit easily, because sometimes it's quite confusing. So first, N, we know that it is a turns, or we put as a T. Then I, we know as ampere. 1, 2, 3, this is a M. So 1, we need to find the H. H is what? Ampere turns divided by meter. So ampere turns divided by meter, or without T, A meter minus 1. Okay, this is H. Or 5, I need to find F. So F is actually turns times A, right? Or this H times M. But usually we use turns times A, become ampere turns. This is my 5. 6, we know that Weber is for only flux. 7, B Tesla, A meter square. It's no issue, right? B Tesla as well. Mu, this is a little bit issue. Mu actually is a mu r mu naught. Mu r, we know that it is a dimensionless. So we focus on the mu naught. Mu naught is actually Henry per meter. So when it's a Henry per meter times dimensionless, it's actually Henry per meter. In another way, we also can put it as a Weber per ampere meter. If let's say we develop it lah. So usually I just use Henry per meter. Next, I need to find the reluctance. So reluctance I did not expand here. I directly put here since I have a F ampere turns, Weber for flux. If let's say I want to find my reluctance, I just use ampere turns divided by Weber. It becomes ampere turns divided by Weber. Also the green box is come here. Red box is come to here. So this is the overall of the things that we need to memorize, so that we can answer. When we memorize these things, we can answer all the equation. For sure, we need to know we need to comply the principle of conservation of energy, where we use the Ampere circuital law, we use the Kirchhoff law, we use something like KCL, KVL, but that one KCL, KVL is applied in electrical circuit. We apply the Kirchhoff law only for the magnetic circuit. So yeah, thank you very much.